Hey everyone, have you ever seen a news report and just wondered, how on earth do they know that? How can they call an entire election with millions of voters by talking to just a couple thousand people? Well, it's not magic, it's a really powerful tool called sampling, and today we are going to pull back the curtain and demystify the whole thing.
Right, this is the big question. It feels like it shouldn't be possible. How can such a tiny group of people possibly speak for millions? Well, I promise you, it's not a magic trick, it's a science. And once you get how it works, you'll see how he makes sense of pretty much everything, from political races to what people are buying to public health trends. It's a fundamental concept.
So here's the game plan for today. We're going to start with the big why we even do this. Then we'll meet the two main families of sampling. We'll get to know the key players in each of those families, talk about some of the common traps researchers need to dodge, and then, finally, we'll tackle that huge question: how big does a sample really need to be?
Okay, let's dive in. First things first. Before we get into all the different methods, the how, we really need to lock down the why. You know, why do we bother with sampling in the first place? This is the big idea that everything else is built on.
It all comes down to these two words, population and sample. Just think of the population as the entire pie. That's every single person or thing you want to know something about. The sample is just one slice of that pie. The whole goal, the entire reason sampling exists, is to pick a slice that is so perfectly representative that by tasting just that one piece, you know exactly what the whole pie tastes like.
So how do we actually pick that perfect slice? Well, this is where we hit a massive fork in the road. You see, pretty much every sampling method out there belongs to one of two big families. And understanding the difference between these two is probably the single most important thing you'll learn today.
Okay, so on one side of the road, you have probability sampling. Think of this like a totally fair raffle. Every single person in the population gets a ticket, and every ticket has the exact same chance of being drawn. It's all about pure, unbiased, random chance. Then on the other side, you have non-probability sampling. This is more like being a casting director. The researcher is deliberately handpicking people based on their judgment or just who's easy to find. It's not random at all.
So let's meet that first family, what I like to call the probability crew. These guys are the gold standard. They're what you use when you want to make big, confident claims about the entire population. And their secret weapon, their superpower, is randomization, which is our absolute best tool against bias.
And the most famous member of this family? Simple random sampling. It's exactly what it sounds like. This is the purest form of that lottery we were talking about. It's literally like putting every single name into a giant hat, shaking it up and pulling names out. Every person has the exact same shot of getting picked. It's clean, it's simple, it's fair.
But what if you need to be sure that certain groups are properly represented in your sample? That's where stratified sampling comes into play. With this method, you first slice your population into important subgroups. We call them strata. So you might divide everyone up by age group, or by gender, or by location. Then you do a simple random sample inside each of those little groups.
Check out this example. It makes it super clear. Imagine a company has 800 women and 200 men. If you just took a random sample of 100 people, you might accidentally get 50 men and 50 women, which doesn't reflect the company at all. With stratified sampling, you make sure the proportions match. You'd randomly select 80 women from the female group and 20 men from the male group. Boom! Your sample is now a perfect miniature replica of the company's gender balance.
And there are a couple other key players in the probability crew. First, there's cluster sampling. This is a lifesaver when your population is spread all over the place. Let's say you want to survey all high school students in a state. That's impossible. But what you can do is randomly select 20 schools, those are your clusters, and then survey every single student inside those 20 schools. It's way more practical. Then you have systematic sampling. This one's pretty clever. You just get a list of your population, pick a random starting spot, and then select, say, every 10th person on the list. It's a simple, elegant shortcut to a random sample.
All right, let's cross the road and meet the other family, the non-probability crew. Now, these methods don't use randomization at all, so why use them? Well, they're often way faster, cheaper, and easier, and sometimes your goal isn't to generalize to the whole world, but to get a very specific, focused snapshot of a particular group. First up, we have purposive sampling. Here, the researcher acts like a talent scout. They use their expert knowledge to deliberately hunt down and select the exact people who have the information they need. You see this all the time with TV news reporters on the street. They're not just stopping people randomly, they're looking for someone who looks like a tourist, or a business person, or a parent with young kids to ask a specific question.
And then there's a really cool one called snowball sampling.
This is your go-to method when you're trying to study a group that's hard to find or hidden. Think about people with a very rare hobby or members of an underground community. How do you find them? Well, you start by finding just one person and then you ask them to introduce you to others they know.
It's easy to see how this gets its name, right? You start with one person. That person leads you to 2 or 3 more. Then each of those people leads you to a few more. And before you know it, your sample size just grows and grows, like a snowball rolling down a hill. It's an amazing way to get an inside look at a community that would otherwise be completely invisible.
Now here's a really important distinction to make, because this trips people up. Quota sampling looks a lot like stratified sampling. In both cases, you divide the population into groups. But here's the absolute crucial difference. Stratified sampling uses a fair, random lottery inside each group. Quota sampling does not. It just tells the researcher, go find me 50 women between the ages of 20 and 30. The researcher then fills that quota any way they can, usually by talking to the first 50 people they find who fit the bill. One is random, the other is all about convenience.
Okay, so we've met the families. But building a sample in the real world isn't so clean and perfect. The world is a messy place, and researchers have to be constantly on the lookout for different kinds of biases and errors that can totally derail their results.
One of the biggest offenders is something called response bias. So imagine you send out a survey asking people how much they like their job. Who do you think is most likely to actually fill it out and send it back? Right, the people who either absolutely love their job or the people who absolutely hate it. All the folks in the middle who just think their job is, fine, they probably won't bother. And if that happens, your results are completely skewed because the people who didn't respond are fundamentally different from the people who did.
And that's really the whole point. Good research isn't about achieving some impossible state of perfection. It's about being smart. It's about understanding these potential biases, planning for them, and doing everything you can to control for them. It's about being upfront and honest about the limitations of any sample.
And this brings us to what is basically the million-dollar question for any researcher. How many people do I actually need to talk to? If you pick too few, your results are worthless. If you pick too many, you're just wasting a ton of time, money, and energy. So what's the magic number?
Well, for experiments, the answer often comes from something called a power analysis. And you can think of it like a recipe with 3 main ingredients. The first is alpha. How much risk are you willing to take of a false alarm, of thinking you found something when there's nothing there? The second is power. How much do you want to be sure you don't miss an effect that really is there? And the third is effect size. Are you looking for a massive sledgehammer-like effect or something really small and subtle? By balancing those 3 ingredients, researchers can calculate the just right sample size they need for their study.
So there you have it. We have this amazing toolkit. We've got the fair and random methods from the probability crew and the fast and focused methods from the non-probability crew. We know how to figure out our sample size and how to watch out for bias. But it all leaves us with one last question to chew on. In a world this complicated, this messy, this diverse, can any small slice of the pie, no matter how carefully we choose it, ever truly capture the full, rich, complex flavor of the entire thing? That's the challenge and the beauty of what researchers try to do every single day.